Alright, so now getting back to the derivation of the volume of this sphere, using thin disks 1 and 2. Now, as I said before, these two disks will have this. We are considering this angle to be so small, this angle d phi to be so small. I'm gonna represent that angle on the other side so I have more room to write the angle. So this angle d phi, and their phi is measured with respect to the vertical line. This is just how it is. It's called, I think it's called azimuthal angle or something else. I don't know. I don't remember the actual name, the technical name. But if this angle is phi, and then in that case these small angles will be d phi, a little very small change in the angle phi. Okay, they can be represented on that side too, it doesn't really matter. So consider this angle to be d phi then. So these two disks are separated by the small angle d phi. Okay, now if that's the case, then the area of these disks, I'm assuming that this change in angle is so small that the area almost stays constant. And so that area of the disk will be pi r squared, where r is this distance. So for this disk, it will be, if this is the radius of the sphere, and if this angle is phi, so if the radius of the sphere at the starting from the line segment representing the radius of the sphere, starting from the origin of the sphere to the edge of the sphere, such that it hits the edge of the disk, then the angle projected by that line segment onto the vertical is phi, right? So if that's the case, this part, this part of this right triangle, right angled at this point, should be rho times sine of phi, right? It should be rho times sine of phi. So the radius of this disk number 2 is rho times sine of phi. This is the radius. Now I can square that radius and multiply it with pi to get the area of this disk 2, right? Now, as I said, I'm assuming this change in angle d phi to be so small that the area of the other disk, the disk 1, will be the same. It will be different. We'll have a different value of phi, but that change is so small that I can almost consider them to be the same. So this, let me just write my pi a little better. So this is pi, and this is the area, pi r squared. Now, in order to get the volume, we need the length dimension, the distance dimension. Oops. I raised the distance. Okay, the distance dimension. So I need that. Now, if this is the disk, if this is one disk, and if this is another disk, right? And you want to add the area up then you have to get the volume, then you have to multiply it with the vertical distance, the distance along which you are translating these disks. So that will be this vertical distance, right? This vertical distance from this point to that. Now, this distance can be represented in two ways. One is you can just say that it's a small change. It's a small change in the distance from the center to the disk. There is a distance from the center to the disk, and there is a small change in that. So you can, that's one way of saying it. So the distance from center to the disk will be, as this is angle phi, the adjacent distance will be rho cosine phi, and the small change in the distance is d times rho cosine phi. So I'm just going to write that down. It's rho cosine phi, that vertical distance, the adjacent vertical distance, and a small change in that, because you're going along the axis, just like dx, a small change in x along the x-axis. So a small change in this x, which is rho cosine phi, along the rho cosine phi axis. I'm gonna call it out that way. Will be d in the bracket rho cosine phi. Okay, so that will be rho being constant. You take the derivative of cosine with respect to phi, and so you have to multiply the phi onto the other side because you're taking the derivative with respect to phi, so you have that. And then in there you have the derivative of cosine phi, which is sine phi, right? Well, it's negative sine. Derivative of cosine is negative sine, right? So that's this vertical distance, small change along this line, right? The dx, if you may. Or you can do the same thing by considering this arc length. Now this arc length is x, and if you want the vertical distance, it can be seen as a vertical component of this arc length, right? Now, if you want to do that by that, I think I'm running out of minutes on my video, so I'm going to pause it here, and I'm going to do another video and show you how you can do the same thing by using the arc length. You can get to the same answer, the vertical distance, the distance, this distance equals that value by using the arc length, okay?